So we've talked about how to find the inverse matrix, but let's talk about how we apply it, how we use it. And how we use it is in solving simultaneous equations using matrices and other ways. So we can use matrices to solve simultaneous equations. Simultaneous equations are two lines that are on a graph. We can have three, we can have four, okay? The solution is where the lines intersect, okay? Where they cross, where they meet. We are looking for the unique solution. So what do we mean by unique solution? A unique solution is, that location of where they cross, okay? And there's just one, okay? Just one, because that's what unique means. It's just one, all right? So you can imagine we have a graph and we've got our two lines, very badly drawn, but that's where they've crossed. Yep, that's my unique solution. So let's look at this example I've set up here. Solve to find x and y. And we've got our two equations set up here. And of course, back in year 10, you've probably solved those algebraically. But let's do them with our matrices. Now, you probably remember from a couple of topics ago where we set up our simultaneous equations as matrices. You can remember we've got a matrix for our pronumerals here, matrix for our answer, our matrix, a square matrix with our coefficients. So I'm going to name these A, B, C, okay, for this example. All right. We want to find the values of B. Yeah, we want to find what x and y are. To do this, we need to solve for B. Okay. So I need you to think about the linear algebra skills that you have. So let's set this up. We've got matrix A times by matrix B equals matrix C. All right. Now, usually, if this was just, an ordinary algebra, we'd go, okay, I'd divide both sides by A, wouldn't I? So I'd divide by A and then C divide by A. But this isn't algebra, this is matrices, okay? So we can't divide, we don't divide with matrices. So what can I do? How do I get B on its own? Because that's what we want to do, isn't it? We want to solve for B, so we need to get B on its own. What I can do here is times A by its inverse. Because you'll remember, if you times a matrix by its inverse, you get left with the identity matrix. Now, here I'm timesing the inverse of A to the left. You can see it's on the left here. Because A is on the left of B, I've got to put the inverse of A on the left. Now, because it's on the left here, it must be on the left-hand side over C. Now remember, what we do on one side of the equal side, we've got to do on the other side of the equal sign. So, because it's on the left, we've got to do it on the left-hand side here. Remembering that the order that we multiply matrices in is very important. So the inverse of A times by A gives me the identity matrix I. So that means I get left with identity matrix times by B equals to inverse of A times by C. Now, remembering that the identity matrix I times by any matrix, you're just left with that original matrix. So that's why we get left with B. So here we've got B equals to the inverse of A times by C. So that I can start to solve, can't I? Because it's B equal to this. All right. So what do I need to do? I need to find the inverse of A. So that was A. And I found X inverse here. And C was that there. Okay, and there I've worked it out all in there. So I times it all together to get my B. All right, so that means that then X is equal to 3 and Y is equal to 1. And you can see I've done some, I can do it on the CAS as well. Fairly straightforwardly as well, isn't it? You know, I've put in the matrix, assigned it to a variable here, and then worked it all out there. Now, the thing here to remember is that not all simultaneous equations have solutions or will work properly. Not all have a unique solution. And this is because not all square matrices have inverses. Okay? This happens when equations are what we call inconsistent or dependent. And this happens when that determinant is equal to 0. So let's go through what they mean. So, inconsistent equations. So inconsistent equations occur when simultaneous equations have no solution. No solution. They don't cross. This means the lines on the graph are parallel with no intersections. You can see here on one that I've drawn up, which is over here, that they are parallel, meaning they're always going to stay the same distance apart and they are never going to cross. So the equations shown in the graph are parallel with no intersection. That set of equations is inconsistent. Okay, so basically there is no solution. Okay, you've got to remember there's no solution there. So these are the equations. I've set them up in the matrix and our determinant is equal to 0. Because that determinant is equal to 0, there's no inverse, so we can't solve them. Okay, now these two equations are parallel. Do you remember why they're parallel? It's because their slope is the same. Okay, their slope is the same. That means that they're going to be parallel. Now the other one, what we call dependent equations. Now this happens when we have no unique solutions. No unique solutions. There are actually many solutions, or an infinite number of solutions. So the lines actually lie on top of each other. They are essentially the same equation. I've got an example here and I'll zoom up a little bit. You can see I've done it on my CAS calculator and you can see the blue line for the blue equation and the red line for the red equation. I've made one line a bit thicker than the other, but you can see that they lie on top of each other, don't they? They are essentially just, dot, 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 dot. Every single dot on both lines is a solution. So there's no unique solution. There are many solutions, or infinite number of solutions. So the equations are actually the same. Okay? So they equal to each other. Every point is a solution, so there's no unique solution. And that's what we're looking for, a unique solution. So let's do some past exam questions. So here I have one from the 2018 Northern Hemisphere Exam 1, question 6. So we're getting to the middle to hard type of questions now. So the solution to a system of simultaneous linear equations is determined by evaluating the matrix product. So we've already done, found the inverse and done the necessary things to figure out our solution here. But we want to figure out what one of these linear equations could be. So how are we going to do that? Okay, so let's think about what the equations would have been. Now remembering that this is the inverse of whatever matrix it originally was. Okay, it's the inverse. This is the answers. Okay. So let's see if we can figure out, well, if that's the inverse, what's the original matrix? So really, to get here, we've got to think about what's happened to that and try to reverse it. So we know when we find an inverse, okay, our inverse of A is equal to 1 over the determinant of A, and then we've switched those, and then we've times those by -1. All right. And then we times that fraction into the matrix. All right, so here we're not seeing any fractions, so I know that that fraction ended up being a whole number. So 1 divided by something would tend to be 1 divided by 1, or 1 divided by -1 would give you a whole number. So that's giving me a bit of a clue. So is there a common factor for all of those? Yes, -1. -1. So I know, okay, -1. 1 on -1. Okay, so let's divide all of those by -1. All right. So, and then let's go back. Let's do one more step and think about, all right, I need to get this back to the original A, B, C, D. So I know that 2 and 4 reverse position, and that these two will be divided by -1. So that's 3, 3. Okay, so that means my 2 possible linear equations would be 2x plus 3y equals 3, or 3x plus 4y equals -1. Okay, so A and B, now I could have crossed them off pretty much straight away because they relate to the inverse, don't they? Yeah, so we're only ever looking at C, D, or E. And let's have a look at that. Now D, I probably could have cut off straight away because they're relating to that B and C, aren't they? They're not the same equation. So again, I was only ever looking at C or E. And 3 plus 4x equals 3. Well, that doesn't match up, does it? That should be equal to -1, so it's not E. So the answer is C. Okay, so we're here with the 2017 exam, question 3, so an easier question. Which one of the following matrix equations has a unique solution? A unique solution. So that means we're looking for where the determinant is not equal to 0. So let's go through. 1 times 1, take away 1 times 1. Well, that's equal to 0, isn't it? Determinant equals 0. Yep. Because that's 1, take 1. So 6 times by 4, take away -4 times by -6. So 24. That's positive. So take away 24, so that's 0. So 8 times 2, take away 4 times -4, so that is 16. That's -16 there, so negative plus 16 equals 32, so it's probably C, but we'll just double check. This one's quick, so 7 times 0 is 0, take away 5 times 0, which is 0, so determinant 0. Yeah. 4 times -3, take away 6 times -2, so that's -12. That's be plus because that's -12 plus 12 equals 0. So yes, C. 63% of the state answered correctly, 14% answered A. Now, I would take that down to people getting confused and thinking they were looking for whether the determinant was equal to 0. And so A is the first one that you would check, and because it was equal to 0, they answered A. Okay, but we're looking for a unique solution, so we're looking for whether the determinant is not equal to 0. So we are, yep. So we're looking for C. Okay. So here's from 2019 Northern Hemisphere Exam 1, question 4, so about middle difficulty. In a game between two teams, Hillside and Rovers, each team can score points in two ways. The team may hit a full or the team may hit a bit. More points are scored for hitting a full than for hitting a bit. A team's total point score is the sum of the points scored from hitting fulls and bits. The table below shows the scores at the end of the game. Okay, so we've got here, your fulls and your bits and your totals and each team. So let F be the number of points scored by hitting one full. Let B be the number of points scored by hitting one full. Which one of the following matrix products can be evaluated to find matrix FB? In other words, we're not being asked to actually solve it. We're just being asked, well, which one of these will give you a solution? Okay, well, first off, I know, let's set this up. It'll look something like 4, 8, 5, 2 times by FB equals 5249. So FB equals the inverse of that times by 5249. Okay. Well, it can't be C, E, or D, can it? Because it's got to look something like this. Okay? It's got to look something like this. And actually, it's A. Straight off A. We don't have to even figure out what the inverse there is. Okay. So, yep, that's how we can use our inverse matrix.